I represent AXT. AXT's been around for nearly 30 years, originally as an X-ray tube manufacturer. We represent about 50 international brands covering areas such as nanotechnology, material science, life science, non-destructive testing and mining. So we've traditionally been into, we say that we have about 50% traditional technologies and 50% new technologies. And because we have sales and service centres across Australia and we have a foot in the door of academic research and industry, we're constantly being asked to take on new technologies. And one of these is Elemission. So Elemission was established in 2014, and the founding members of the company come from the Canadian NRC, which is similar to our CSIRO. They're experts in LIBS, chemistry, chemometrics, engineering physics, optoelectronics and lasers. And being a new company with new techniques, they've aspired to have the most modern up-to-date software, and their instruments are based on, driven by C++ programming. So my talk today is on LIBS. And what is LIBS? LIBS is an acronym for Laser-Induced Breakdown Spectroscopy. So the takeaway is that it's a laser-based instrument for mineral analysis, and it analyses all elements. It's exceptionally sensitive to light atomic number elements, and this is as compared to X-ray technology, which is insensitive to light atomic number elements, for reasons that Mikhail said, that the fluorescence that comes off is quite weak. So LIBS uses slightly different photons within the atom, and I'll go into that in a minute. So it's a near-instant analysis, so the analysis is virtually at the speed of light. Again, that's a little bit different to XRF analysis, where, all right, it's an instant analysis, but you need to have long counting times to acquire all that spectra. There are different instruments available that can analyse solids, liquids or gases. And it's microanalysis, whereas generally an X-ray beam is larger in diameter. Well, it depends on what instrument you want, but the routine industrial use instruments, they have a wide area X-ray beam, whereas the X-ray beam for LIBS is typically in the order of 50 to 100 microns. And the detection limit is low ppm to high ppb. So the timeline for LIBS closely mirrors the timeline of the development of lasers. So a laser is a parallel beam of light. So Einstein had the concept in the 1950s that light, which is normally going out in all directions, similar to his hair, could be made to be convergent and synchronous. And so a laser is a parallel beam of synchronous light. They were patented, laser technology was patented in the 1960s with the Nobel Prize awarded in 1964. And ever since then, as lasers have continued to develop, the uses and applications of laser technology has grown. So if you look below the wave, the laser line wave, 1992 we had CDs for listening to music. 1997 the old speed camera used to be a photograph, and then now it's laser technology. And 2006 surveyor's theodolite became laser-based. Looking above the laser line, you have uses where the energy of laser power is harnessed for destructive or minimally invasive techniques. So you've got laser eye surgery, laser cutting and welding, and LIBS technology, which is minimally invasive. It interacts with the surface of the material. So the LIBS phenomena was identified in the 1960s when the lasers were first invented. They remained in the realms of really niche applications, university and academia, up until the probably about the early 2000s. So one of the first instruments that was commercially developed is what you see above the timeline there. I don't know how to work this thing. Is that a laser light? How do you make that work? The little one. Slide, yep. Oh yeah, so they were big, clunky instruments. They first came to the attention of the mining industry in 2012 with the landing of the Curiosity rover on Mars. SciAps launched a field portable instrument in 2015 for alloy applications, and then they developed the mining applications a few years later. Outertech have got an on-stream analyzer that they developed in 2015. So Elemission launched the Coriosity in 2017. So the Coriosity is for core analysis, which is what I'm going to talk on today. In 2018, they launched an on-belt analyzer. Earlier this year, it was a slurry analyzer. And interestingly, the MinEx CRC, of which Elemission is not involved, but they're currently working on a LIBS-based system for downhole analysis. So LIBS technology really is advancing very quickly, and it's the convergence of a whole lot of different technologies that are making LIBS technology more useful now. So how does it work? So you have typically a neodymium YAG laser that puts out the laser light, parallel beam of light. It goes through a series of optics, focusing lenses, and that wide laser beam is focused onto the sample, where it interacts with the sample, and it causes a plasma. So plasma is in the order of 6 to 10,000 degrees, and it's a little microplasma. Femtograms of material are ablated. So elements jump up into an excited electronic state as they absorb energy from the plasma, and then as they return to their ground state, they emit photons which are recorded, they're angularly resolved by a spectrometer and a detector. Now, every element has its own characteristic wavelength. Typically, there's more than one wavelength, and some elements like iron have trillions of elements. So every element on the periodic table can be analysed by LIBS. Now, the elements on the left-hand side of the periodic table are more sensitive to the elements than the right-hand side of the periodic table. And it all comes down to how ready they are to release an electron. So the elements on the left-hand side of the periodic table are quite happy to give up an electron, but the elements on the right-hand side of the periodic table really don't like to give up electrons. So a plasma is the fourth state of matter, where you have, so the three states of matter are solids, liquids and gases. A plasma is that fourth state of matter where you have basically an electron cloud whizzing around electrons, ions and then recombination molecules. So just touching again on the Mars rover. So the Curiosity rover landed on Mars in 2012. In that time, it's generated about 500,000 spectra. So since comparing 2012 to now, the Elemission core analyzer generates 500,000 spectra in about 8 minutes. So that's how technology has really moved on. And on the success of this, they've got a supercam going on the 2020 mission. So the way this instrument works, it has two lasers. One laser that determines how far away the object is, and then that gives the information back to the spectrometer of where to focus the analytical laser. See, the analytical spot size for the Curiosity is 500 to 800 microns. And everything happens within this head of the instrument. So LIBS works on what's called dichroic optics. So the laser light of 1064 nanometers will go through or be bounced off certain components of the optics, and the returning light goes the opposite way. It goes through or is bounced off the other optics. Most of this instrument is made up with a little nuclear reactor. So I've often been asked, does this instrument exist for mining operations in Australia or underground? And unfortunately, no. Oh, and that's not made by Elemission. So are there existing LIBS instruments out there for minerals? So I mentioned the SciAps instrument beforehand. So that's a little field portable instrument, similar in form factor to the handheld XRF. So they have everything inside the instrument with and typically an Android operating system. So the advantages are that they're field portable and they're lightweight. Now the thing is that they can analyse a discrete spot of 50 microns, or you can raster over a sample to get a larger analytical area. Or this particular instrument has smarts in it where you can interrogate the spectra. Now 50 micron spot size for a geological non-homogeneous material, when you want to get a representative answer, it's not the same as XRF. Okay, it does give you light elements. So what SciAps have done is that they raster over a larger area and then they give you an average of those wider points, or you can use it for mapping. And so in mapping, it gives you element heat maps. And so it's limited to 256 points. So Elemission have come at it from a different angle. So rather than trying to get a field portable instrument, they've gone for extremely high analysis rates to get a micro-analysis on a macro scale, so to very quickly build up a picture of what's going on. So because of the advances of technologies, so typically being lasers, laser fibres, optoelectronics, digital pulse processing boards, because there's a huge amount of information that comes out of these instruments, the publications on LIBS technology has grown exponentially over the last 25 years. So I think I'm suffering the same problem with the video not starting. Oh, there we go. So there are a few companies out there that do LIBS technologies, and if you look at the number line below, so you've got Applied Spectra, they have instruments that operate between 0.2 hertz, 1 hertz. Lyon University in France, 10 hertz and 100 hertz, and Elemission are at 1,000 hertz. And so this is the difference between a 20 hertz system versus a 1,000 hertz system. So when you're analysing core, you've got a lot of meters to analyse. You want to have the highest analytical rate as possible so you can get through as much core as possible. So with a 1,000 hertz analytical rate, 1,000 hertz laser, that corresponds to 1,000 analytical spots a second. So you're very quickly building up a picture, a micro picture on a macro scale. The way it works is the focusing lens rasters the laser across the sample. So it's typically a largest area that can be analysed at any one time is a 40 by 40 millimetre grid. The software interrogates the spectra, corresponds the wavelength to the intensity, and you get mono-elemental mapping. These are all combined using principal component analysis to get multi-element mapping. So it's quite a different approach to XRF core logging. So XRF core logging is typically a larger area, and then they're stitched together. So XRF core logging tends to be more the average, and it works great if you have large-grained minerals. So if you have fine-grained minerals, albeit not less than 50 microns, the LIBS technology is good for that. So this is an example of the Coriosity in action. So it analyses 40 mils maximum at a time and moves the core along. So see in the bottom right-hand corner the spectra coming off. That's the frame rate of the video is 100 images per second. So the actual spectra is coming off at 1,000 analytical points a second. And so every one of those peaks corresponds to an element. An element has more than one peak. But equally, because you're analysing at 50 microns, that elemental signature corresponds to a mineral signature. So it's similar in scanning electron microscope technology where the mineralogy is inferred by the concentration of the elements to each other. Now we heard Mikhail, we saw up there on the screen before, he had the mode of operation of XRF. So when you shoot an X-ray beam into an element, the ones that the electrons that are ejected that we typically analyse are from the inner electron shell. And so being in the inner electron shell, they're not overtly influenced by what other atoms are around it. So you can have like an iron sulfide and you can't tell from it which iron sulfide it is. Because LIBS technology uses the electrons on the outer orbital of an atom, they are greatly influenced by the atoms that are next to each other. And so as years gone by, this has posed problems with quantification because peak height varies depending on the elemental bonding. But with modern day multivariate chemometric software, you can, with a good training set, you can take all those different factors into account and you can quantify it. But additionally, you get mineralogical information. So when you look at that elemental fingerprint, you have a lot of different things going on because all the elements are influenced by what's around them. And so you're more able to build up a mineralogical picture. So an iron sulfide, which might have the same elemental concentration as other iron sulfides, you can determine because the chemical bonding is different, and then you get a slightly different LIBS signature. Because LIBS can analyse for light elements, we're focused on the lithium industry, and this is an example of some lepidolite core. So you see in the dark zone here, you can see very, very high lithium. The white zone here, it's got no lithium, and the pink zone has got a minor amount of lithium. And so each one of these can be quantified, so you do need to have a matrix match calibration. For the handheld instrument, for the core instrument, you just need a good training set with a multivariate analysis, lots of different minerals in your training set. But equally, those fingerprints can be used to infer the mineralogy. This is another example of different mineral fingerprints, so chalcopyrite and sphalerite. The blue is the sphalerite, the orange is chalcopyrite. So going back to that other piece of core before, this area here scanned is a 40 by 20 millimetre area, and it took 3 millimetres to analyse it at full resolution. So full resolution is where you've got your 50 micron spots all next to each other, or if you want a faster analysis, you can spread it out. So the top image is a rainbow of element maps, so lithium red, sodium green, potassium blue, and then where the colours you have the two elements appearing together, you get a bit of a rainbow of colours. This bottom image is the principal component analysis. So that's where it's looked at those areas of similar chemical fingerprint and then domained them all together. So visually it looks very similar to actually looking at the core, but equally you can see the element maps mirrored in that. Now I've got a whole series of different lithium minerals that have been analysed. So top left-hand corner, the principal component analysis of the image. 3 different elements superimposed here, and then you've got individual element maps, with lithium being over here in the red. So lithium is a light element on the first row of the first family of the periodic table, and rubidium being a heavy one. So an 8 by 8 millimetre area takes 26 seconds to analyse. Now, the other thing I didn't mention about LIBS technology, so it's a laser beam that's focused, and you expect that focal point to be a discrete distance away from the laser beam and lens, but they have this zone of confluence where it's actually focused within a large area. And so for LIBS analysis, for the Coriosity LIBS analysis, the surface doesn't have to be polished or smooth. It can be uneven. There's a 6 millimetre area of confluence where if you have rough core, it still analyses your sample. For their on-belt analyzer, it's actually got a 140 millimetre area of confluence because the lasers change the optics. Here's some jadarite. What's interesting to note from this sample is, both lithium and boron are being easily resolved by LIBS. So I mentioned that LIBS has been from the convergence of technologies, and one of these is laser technology. So for LIBS, the laser excites the atoms form they go into a plasma, and then as the elements return to their ground state, they emit photons. So you need to have a pulsed laser. So if you've got a laser as a continuum, you've got a continuous burst of light, which you can't do anything with. But with the pulsed laser, you shoot it at the sample, you get a plasma, the plasma breaks down. Shoot it at the sample, plasma breaks down. And you also need to have a high peak intensity, so pulsed laser with a high peak intensity. And so when we first started talking to Elemission, I sent them over some very challenging samples, including that lithium core, the lepidolite core. Initially, with the laser that they had on their system, they couldn't get lithium. They worked with the laser manufacturers, got a higher peak to pulse power laser, and they could analyse for lithium. So here you can see lithium and boron in the oolites, whereas the surrounding host rock has got a lot of other different elements. So muscovite, 15 by 15 mil area, 50 micron spot size, so that takes 90 minutes to analyse. So you really do get a picture of your element deportment because of that small laser spot size. This is some zinwaldite, and note cesium as a heavy element is detected too. Can also analyse for gold. Now the issue with gold is that gold tends to be submicron particle size and it's not evenly distributed in the sample, but if gold is in the area that you're analysing, it detects it. So it comes down to how do you quantify it. So it's a surface analysis. It doesn't suffer. So there's two ways of looking at a surface analysis. One is that, well, how representative is it of the bulk of the material? But the other way of looking at it is that what you're seeing is what you're analysing, and you're not getting an interfering signal from underneath. So one of the things that happens with X-ray technologies, we saw the depth of penetration graph before. So for a light element, the area of analysis is submicron surface area of analysis, because the fluorescence that comes off is quite weak and it's absorbed by air. But equally, if you've got a heavy element like lead or uranium, the signal for that can come at 5 or 10 mils from the depth of the sample. And so you end up with mixed signals from different elements. So with scanning, I can go on ad infinitum about that, because we also do scanning electron microscopy techniques, and so mixed spectra is a nightmare. So Elemission, they stitch the core together. So at the moment, the core Coriosity analyses 30 centimetres length of core. It takes them 40 millimetre sections at width, and then it stitches it all together. Now next year, they're going to be launching a core tray analyser based on the same techniques as this. And LIBS nowadays really is a convergence of technologies. So pulsed lasers, laser fibres, optoelectronics, digital pulse processors, chemometrics, laser optics, laser fibres. So the software is not advanced as what we have seen in the two previous presentations. So at the moment it's elemental deportment with mineralogy, but software advances are coming along at a great rate of knots, and with the core analyzer you'll be able to have mineralogy, quantitative mineralogy, chemistry, quantitative chemistry, and then likewise element deportment within the mineral, so how much element is within each mineral. Any questions?
Oh, thank you. This is truly exciting technology. Just a question, the laser wavelengths that you use, do you know what wavelengths you're working at?
The laser wavelength is 1064 nanometers.
1064.
Yeah.
Okay.
Now the wavelengths that come off the sample, there's various spectrometers for the instrument, but so the one on the Coriosity is 220 to 820 nanometers, which gives you most of the periodic table. The elements that are outside that range, such as sulfur, you're actually able to determine by molecular lines, molecular banding lines. So that's the thing with LIBS, is that in that plasma you have elements, ions, and then molecules that form. And so it depends exactly on where you take the reading. So plasma burst to the signal coming off, and so it can be optimized for different things.
And then just another two questions. The first one, the distance between the spectrometer and the surface of your core?
Now I'm not too sure, but it's probably about 20 centimeters.
Okay.
Yeah.
And can you also, do you have to work on a flat core surface, or can you work on the...
No, as long as it's within that 6 millimetre area of confluence. So if it's cut core, you can analyse the whole core, but if it's whole core, you would want to restrict yourself to a 1 or 2 centimetre strip down the back.
Thanks.
Is there a required sort of light to actually do the analysis with? Can it work sort of like in broad daylight, or does it need a certain
yes, so the core analyzer is in a box at the moment. So the laser is a class 1 laser, a class 3B laser, which means that if you were to shoot it at you, you'd get little micro explosions on yourself. So it's inside a box that's totally interlocked. So for the on-belt analyzer, it's similar to X-ray technology on-belt analyzer, where it's just it's got flaps that go down it. So it doesn't need lead to shield it. The laser is easily absorbed by other material. Being a laser, it does reflect off surfaces, so specular reflectance, so that's one of the safety issues. So inside the box, inside the Coriosity, it's totally all shielded, but for a non-belt analyzer, it does need to have big, thick black rubber bits down the outside.
Just on that, do you envisage it being able to be taken to site like the other
Oh yes,
instruments?
yeah. So it does weigh 100 odd kilos, but I've had requests to separate the electronics from the optical aspects, which will make it quite easily field portable. So Elemission as a company, they keep on coming up with new advances, and they're quite open to suggestions on different ways that the technique can be used. So a little bit bulky at the moment for the instrument that we've got, that those of you who are coming to see us tomorrow, but yeah, they've said that it's relatively easily separated to make it more field portable. Will?
Excellent talk. Given the challenges with quantification and the sort of increased complexity with XRF, have you done a comparison between the accuracy of the two different techniques?
No, we haven't. And at the moment, elemental quantification across core is still being worked on. So there's different ways of doing it. So you can do it as a line scan plot, similar to what we saw with the XRF technology, where you sum across the line and then you just get the quantification over the line. Or you can go more TEMA style scanning electron microscopy, where you look at the area that you've analysed and then sum the area. But no work has been done on that yet.
So I'm curious about the scanning speed. So how many meters per hour is the carrier?
If you were to do full resolution, so 50 mils next to 50 mils, it would take you about an hour to do a 30 centimetre length of core. If you spread your spacing out both horizontally and then down depths, it would be a lot quicker. So yeah, again, two different thought processes of one where you do a wider space resolution and then you go back and you do a finer resolution on areas that look interesting. I've had the fellows at Codes in Tasmania who specialise in ICP-MS think that this is going to be a great complement to that, where they can analyse the entire core by LIBS, so LIBS, which is laser-induced breakdown spectroscopy, so it uses a laser to get an OES type signature, and then areas that are of particular interest they'll cut out and then do laser ablation ICP-MS spectroscopy. So you can either use it for bulk analysis of core or microanalysis of core. A lot of data that comes off, a lot of data.